vessels and the lymphatic system. And I'll post that today, and you'll have a week to do that. So that's kind of where we are on that. Right. So I'll share my screen. We'll get back to that PowerPoint we were on. All right, here's where we left off. We left off talking about immunity. We spent a little bit of time on innate immunity. So I went over some of the different non-specific things that we're born with, that are basically chewing up and finding things and fighting against things that are non-specific, fighting against things that just don't look right. What we will talk about today is the adaptive immunity. Right? It's specific. It's specific against a particular pathogen, so a certain virus or a certain bacteria. And there are different types of active immunity, or different types of adaptive immunity. There's active and passive. Active develops after you are actually exposed to the pathogen. Passive is actually where you are just receiving antibodies from another source. Well, that's the biggest difference between active and passive. Active is activating your own immune system, like a vaccine does, or like actually getting sick with something does. Whereas passive, you are just getting antibodies from somewhere else. You're not activating the person's own immune system, but they're still protected as long as they have some of those antibodies. Now, passive can be natural or artificial. An example of natural would be the antibodies passed from a mother to a newborn infant during breastfeeding. Artificial, they can actually take antibodies from a healthy individual and inject them into somebody who's sick, just to give them temporary immunity to something until their own immune system is strong enough. Active immunity can also be natural or artificial. Natural would be, just getting whatever sickness that is, whatever illness that is. Chickenpox, for example, if you get the chickenpox, you are immune to them after you get them once because you've had them. Artificial acquired is something like a vaccination and immunization, where they inject something into you that activates your immune system against a particular pathogen. So you have immunity because your own body builds its immunity, but it's artificial. You didn't actually get exposed to the illness. It's usually a modified form of the virus or of the bacteria, whatever you're getting a vaccine against. This adaptive defense, it's always specific, right? It's always looking for specific antigens, specific markers on the outside of a cell. And there are two separate wings of it, or two separate branches of it. One is called cell-mediated and one is antibody-mediated. Cell-mediated immunity or cellular immunity is always T cells, okay? Antibody-mediated, which is also sometimes called humoral mediated or humoral immunity, is always B cells. The big difference is that T cells can actually go out and kill certain pathogens. B cells cannot. B cells make antibodies, and antibodies kind of target the pathogen for destruction by other cells. And that's what we'll see. That's the biggest difference. The T cells and B cells are both lymphocytes. They're just two different types of lymphocytes. Remember, the T stands for thymus. T cells develop in the thymus. B cells develop right in the bone marrow. So they're born and they stay right in the bone marrow and develop into B cells. So adaptive immunity, just by the nature of it, it's not present at birth. It's something that you can develop over time. It can be either active or passive. Like I said, you either can be exposed to a certain virus or pathogen and develop immunity to it, or you can be given vaccinations, which exposes your immune system to a variant of that virus, which will help you develop immunity to it. Okay, so there's active immunity, naturally acquired and artificially acquired, which I've talked about already. Passive immunity, again, can be naturally acquired or artificially acquired. So properties of this adaptive immunity. One is that it's specific. I keep saying that. It's very specific. It's not just looking for things that don't belong, things that don't look right. It's actually specific to a particular antigen. Another property of it is that it's very versatile. We produce millions of different lymphocytes, and each different lymphocyte has a different antigen receptor on it. Okay, so you've got all these inactive lymphocytes, all with different receptors, and each receptor is specific. It's a very specific shape, and it would only bind with one antigen. And it's only when that lymphocyte sees that antigen that matches up with its receptor, that lymphocyte will clone itself and make up an army of cells. And that's what we'll see in a minute. Adaptive immunity always has memory as well. So the other part of the immune systems don't. What that means is that when you are exposed to a particular antigen, you make up an army of cells to fight it. Part of that population are memory cells, and memory cells stick around for years. And the reason that memory cells stick around for years is that if you ever see that antigen again, you have an army ready to go. You've already cloned that army. It's already ready to go in your body. And adaptive immunity has tolerance. And all that means is that it recognizes your own cells versus foreign cells. So remember, all cells have markers on the outside. Those markers are called antigens. So your own cells have antigens, foreign cells have antigens, bacteria cells have antigens. The immune system, the adaptive immune system, has the ability to see whether those antigens are your own or not, right? It sees all these antigens, all these surface markers. And if they're surface markers that are part of your own cells, it leaves them alone, right? Your immune system knows not to touch those, but it will go after any antigens which are not self. Okay, so again, adaptive immunity can be cell mediated or antibody mediated. And what happens when you trigger one, it triggers the other, right? So there's this communication and feedback arrows going back and forth. In other words, if you trigger B cells, if something activates the B cells, they are then going to signal T cells. Hey, look out for this antigen. It's here, it's in the body. If you trigger T cells, they're going to communicate with B cells to look out for this particular antigen, right? So that you get the strongest response possible. You don't just get just T cells attacking or just B cells attacking, you get both. And T cells can undergo this direct physical and chemical attack. They can actually bind to the cells that have these foreign antigens and attack them. And we'll see how that happens. B cells don't do that. B cells actually produce antibodies, and antibodies basically bind to these antigens and target them for destruction by other white blood cells. So what is this whole antigen recognizing process? Well, so you have T cells in your body, right? You make millions of T cells. Each T cell has a slightly different receptor. The receptor is there and it's particular to any potential antigen that you might see, right? So your body makes up millions of T cells and they make up a different one for each potential antigen that you might see. They're inactive, and they're inactive until they see an antigen that matches up with their receptors, right? So in order for a T cell to become active, it has to bind to a specific antigen. Now, T cells cannot recognize antigens just floating around in your body, right? So you have bacteria cells, you have viruses in your body, and as they're floating by, T cells won't necessarily recognize them. What they need is what are called antigen presenting cells. Antigen presenting cells are other white blood cells, other non-specific white blood cells, okay, like dendritic cells, and macrophages. These are usually derived from monocytes. These cells go up and they chew anything that doesn't belong, right? They're non-specific. They look at something and they say, oh, that doesn't look right. Let me chew that up. When they do, right, when they chew up that bacteria cell, they take the antigen, the marker that was on the outside of that bacteria cell, and they don't destroy that. They grab that and they put it on the outside of their own cell, right? So they chew something up and they say, I wish I had a good picture of it. They don't. They chew something up and they say, oh, this cell had the red triangle on the outside of it, right? So they chew it up and then they take the red triangle and they hold that up for the rest of the immune system to see that if you see anything with this marker on the outside of it, you have to attack it, that it's bad. Those are antigen presenting cells. The only way T cells become activated is if they are presented with the antigen by an antigen presenting cell. So in other words, if the bacteria just floats by and it has a particular antigen on it, the T cell won't necessarily see that and recognize it and be activated. But if a white blood cell like a macrophage chews up something and it takes the antigen from what it chewed up and it puts it on the outside of its cell, it's showing the T cell, look for this antigen, right? And go out and kill anything, destroy anything with this antigen. Then the T cell recognizes it. So what this is talking about here is that T cells have the ability to see class 1 and class 2 MHC proteins. Class 1 MHC proteins are, MHC stands for major histocompatibility complex. MHC proteins are the self antigens, the antigens on your own cells, right? So T cells recognize that the MHC, the self antigens are there. They're going to leave those cells alone. But class 2, right? Class 2 cells are those non-specific white blood cells that can chew up something and take that antigen from what they chewed up and put it on the outside of themselves. So they can be antigen presenting cells, right? So the T cells are exposed to an antigen presenting cell, and then they're activated and initiate their immune response. Okay. There are different types of T cells. There's basically a couple types that you need to know about. And it's dependent, the way that they are seen, the way that they're divided is basically by what are on the outside of those T cells. There are cytotoxic T cells and helper T cells. Cytotoxic T cells are sometimes called CD8. Helper are called CD4. Okay, and that's basically just what the markers are on the outside of the T cells themselves. Cytotoxic T cells can respond to antigens in class 1 MHC proteins. So cytotoxic T cells are the ones that recognize your own self antigens. Helper T cells respond to antigens on class 2. What this means is that the antigen presenting cells can activate the helper T cells. Helper T cells then can activate cytotoxic T cells. Once these T cells are activated, they differentiate, right? They clone themselves. So you get a bunch of cytotoxic T cells, a bunch of helper T cells, a bunch of memory T cells that'll stick around for years, and suppressor T cells, which will suppress the immune system from acting further. CD8 cells are killer cells, right? Cytotoxic T cells. Cyto means cell, toxic means killing. Once these are activated, they clone themselves so that you have more cytotoxic cells and memory cells. So they destroy bacteria and fungi, okay? They actually can do a bunch of different things. They can release these chemicals that poke holes in the bacteria, right? They secrete cytokines, which activate a process called apoptosis, which is programmed cell death, like cell suicide. And they secrete these lymphotoxins, which disrupts the cell's metabolism. So cytotoxic T cells can go out and actually kill off cells that have this antigen. Right? And so here you can see what you have is some sort of virus here, which has an antigen on the outside of it. An inactive cytotoxic T cell might recognize that antigen and clone itself. And when it clones itself, it produces more cytotoxic T cells and more memory cells, right? And it can go out and actually destroy any cells that have that antigen through these different means. Helper T cells cannot do what cytotoxic T cells can do. They cannot go out and actually destroy the other cells. Once they are activated, they divide into more helper cells. Now they secrete cytokines, which call over other white blood cells, and they can stimulate the cytotoxic T cells and the B cells, right? So that's what helper T cells do when they get activated. So both cytotoxic and helper T cells make memory cells when they're activated. Those memory cells stick around for a long time. And what happens is if you're ever exposed to that same exact antigen again, you already have an army ready to go, ready to fight. And most of the time, you won't even get any symptoms from that pathogen with that antigen because you mount a defense so quickly and so strongly. Regulatory T cells suppress the response of other T cells and B cells. So kind of when they've done their job and they've gotten rid of whatever's infecting you, you secrete these things called suppression factors, which slow down the production of more T cells and B cells. So that's how T cells work. Now, B cells work in a similar manner. With B cells, you produce millions of different B cells. Each has a different receptor, and that receptor is very specific to an antigen. Okay, so just like T cells, they stay inactive until that receptor binds to an antigen. But they don't need antigen presenting cells. They don't need APCs. They don't need the other white blood cells to come along and chew something up and hold up the antigen. They can just see these antigens, right? They can recognize these antigens, and they can recognize the difference between your own antigens and the antigens of something that's not your own cells. So when a matching antigen appears, the antibodies bind to the antigens, right? And you clone these B cells and you make more and more antibodies. Now, the B cell is then also activated by helper T cells, right? We said the helper T cells can activate B cells. The activated B cells divide into plasma cells and memory cells. So just like your T cells, you have memory cells that stick around. Plasma cells stay in the bloodstream, as plasma suggests, and they secrete large amounts of antibodies. What B cells do is they make these proteins called antibodies. They don't go out like T cells do and actually kill off other cells. But these antibodies will bind to the antigen on the foreign cell, and you'll end up with these clumps of antibodies bound up to these antigens. And that clump does not look right to a white blood cell, right? And so a different white blood cell will come along and chew that up. So here is an example of an inactive B cell. It's got all these receptors on it, right? Those receptors on the inactive B cell, those are actually antibodies. And when an antigen binds to one of those receptors, right? The antigen in this case is the red circle. Once it binds to that receptor, the B cell is activated. They call it sensitized, just means activated. When it's activated, when it's sensitized, it can clone itself. So not only does it clone itself, it can activate helper T cells. So just like helper T cells activate B cells can activate helper T cells. right? And that's what this is, the co-stimulation, they activate each other. And then you get a cloning effect. You get all these memory B cells, you get activated B cells. The plasma cells go out and secrete antibodies. So these proteins that look like Ys they're just proteins that are in your bloodstream. And they are really, really specific to only one antigen. So in this case, it's this red circle antigen. So these antibodies are going to bind to any cell that has that red circle antigen on it. And they're going to cause it to clump up, right? So you might get a cell, might have 10 of these antigens on the surface, 10 of these red circles on the surface. All of a sudden you get 10 antibodies bound to that one cell. And so now that's traveling through your bloodstream or through your lymphatic system. And the white blood cells, the non-specific white blood cells, are going to see that, right? The macrophages are going to see that, and they're going to say, well, that doesn't look right. There's a bunch of antibodies bound to that. There's a big cluster, a big clump. We better chew that up. And that's really what antibodies do. They target those cells to be chewed up by other cells. Okay, so here is a nice table, right, that summarizes cells involved in tissue defense. This first part here, neutrophils, eosinophils, mast cells, these are cells that are part of the non-specific white blood cells, part of your innate immune system. The difference between that first table and the second table is that in the second table, you have macrophages and dendritic cells, sorry. And macrophages and dendritic cells can serve as antigen presenting cells. So these APCs, these are just, again, just non-specific white blood cells, but they can chew up something, take the surface marker, hold it up on their own cell, and in doing so, activate T cells, right? That's what macrophages and dendritic cells can do. Neutrophils, eosinophils, and basophils cannot do that. And then the actual lymphocytes that we have. Well, we have natural killer cells, which don't really have to be activated. But we have cytotoxic T cells and helper T cells, right? Cytotoxic T cells can go out and kill cells. Helper T cells activate cytotoxic cells, or they activate B cells. B cells actually produce antibodies. They can activate helper T cells as well. Regulatory T cells suppress the immune response after a certain amount of time. And then you produce memory cells. Both T cells and B cells produce memory cells, and those stick around for a long time. Okay, so here is a much better summary of what's going on. Right? So you've got antigens, right, that trigger the response. So here you've got 3 different types of pathogens, right? 3 different types of things that might infect you. Over here on the left, this pink thing is probably a bacteria cell. These 2 look like viruses. No matter what that pathogen is, it has a marker on the outside, and that marker is called an antigen, right? So these red circles or these blue circles are antigens. Those antigens are going to be what trigger the immune response. Now, non-specific immunity we talked about, right? Complement, natural killer cells, macrophages. They're not looking for any particular antigens. Remember, macrophages can take, when they chew up this bacteria cell, they can take these red circles and put them on the outside of themselves and show it to the T cells. That's called antigen presentation, right? Macrophages can do that. And that triggers the adaptive immune response, okay? Which is where you either go through T cells, right? Or B cells. And there's a lot of crosstalk here, right? These T cells can activate B cells. These B cells can activate T cells. The bottom line is you're destroying the antigens. You are getting crosstalk between everything, right? You're getting non-specific and specific immunity cross-talking with each other so that you can get the best, strongest immune response possible to try to fight off whatever's infecting you. Come on. There we go. I don't know why it won't let me go to the next slide. Sorry about that. There we go. So what you end up with is something called the primary response and something else called the secondary response. This is due to memory cells. So remember, when you activate T cells and when you activate B cells, part of what happens is you make these memory cells that stick around. So the first time you are exposed to any pathogen that has a specific antigen on it, right? Remember, antigens are the things on the surface of the pathogen. Anytime you see it, an antigen for the first time, that's your primary response. Your first exposure gives you your primary response. And if you look at this line, what this line is showing is antibody concentration. So it's just an arbitrary amount, right? It's not an actual number. But they're saying in about 2 weeks, so about 2 weeks after you're exposed, you're producing the highest amount of antibodies against that particular antigen. So it's going to take your body a couple of weeks to clone up enough B cells to make enough antibodies to fight off this thing, right? And hopefully you do, hopefully you fight it off. But then look at the second exposure. Second exposure triggers what's called the secondary response. The second exposure, within a couple of days, you've reached the same antibody level as your primary exposure. Within 2 weeks, look at how much more antibody you produced. You produce like, this is usually a logarithmic graph, so you produce like 10 times more antibody. So what happens is the second time you're exposed to something, you produce a much stronger, much quicker response. And usually you won't even feel any of the symptoms of it, right? You won't even know that you've been exposed to that particular pathogen because you won't feel any of the symptoms. You won't feel like you got sick at all. This is the thought behind why vaccines work, why immunizations work. What they're doing when you get that shot, they are triggering this primary response. So in that shot is usually it's usually a modified form of the virus, right? Or whatever's infecting you. And so it's triggering your own primary response so that you have an army ready to go. So that if you are ever exposed to it, right? Like right now they have the vaccine for varicella, for chickenpox. So you get that vaccine, it triggers this primary response. If you're ever in a situation where you are exposed to that virus, the secondary response is triggered and you won't actually get infected. You won't actually feel any of it. Okay. That's the whole purpose behind something like a vaccination. Now, the rest of the chapter goes into a little bit about abnormal immune responses. So all of this that we've been talking about, of course, is, ideally situated, the immune system works this way. Well, it doesn't always happen that way. Right? There are situations where there are abnormal immune responses. One would be autoimmune disorders. So remember, I said your own cells have antigens on the outside and the immune system recognizes those as your own cells. Well, what if your immune system sees your own cells as foreign, right? It sees that as a foreign antigen on your own cells. That's when you end up with an autoimmune disorder like rheumatoid arthritis or type 1 diabetes. In the case of type 1 diabetes, the islet cells in the pancreas are destroyed because the immune system doesn't recognize the marker on the outside of them. In rheumatoid arthritis, antibodies attack your connective tissue around your joints. there are other, Crohn's disease. This happens in the digestive system. So that's what autoimmune disorders are basically, right? It's basically that your B cells are producing antibodies against your own cells. Usually it just happens with one tissue type, right? It's usually not like all the cells in your body. It's like I said, digestive system or the pancreas or, your joints, things like that. Immunodeficiency diseases. There are certain diseases that attack your immune system. So SCID, severe combined immunodeficiency diseases, that's something that a lot of labs use animals that have this disease in order to test things in them, like mice that have SCID. But what's more common, obviously, in people is AIDS, acquired immunodeficiency syndrome. It's a result of viral destruction of helper T cells. So AIDS has been shown to be caused by the virus HIV, and HIV destroys helper T cells. Now, based on what we just learned, that means you can't really activate cytotoxic T cells very well or B cells very well if you don't have very many helper T cells around. And so it destroys your immune system, right? And people with AIDS usually die of a secondary infection. So they have AIDS, which is a condition, right? But then they get some other infection that most of us can fight off, like pneumonia, which ends up taking their life because they can't fight that off. They can't mount the attack against that disease. And then allergies, which are really common. Allergies are inappropriate or excessive immune responses to antigens. It's called hypersensitivity. Hyper means over. So it's just when your immune system recognizes, pollen from a flower or, venom from the bee, it recognizes as something that's really, really serious, and it mounts this huge immune response. And the symptoms that you feel are because of the immune response, right? You feel a lot of the inflammation symptoms. They can cause, things like your throat to start to close up, right? Anaphylactic shock in severe cases. So it's just an overreaction. It's just your immune system overreacting to something that's not harmful to you at all, right? It's seeing something like pollen as the same as a virus that might infect your body, and it's mounting this huge immune response to it. That's what allergies are. So that's the end of that chapter. What I'm going to do this afternoon or later this morning is post the exam, the next exam. I'll give you guys a week to do it, and we will meet again on Friday. So I need to post the next couple of lectures as well. We'll meet on Friday to start talking about the respiratory system. So I think respiratory and digestive are the next two lectures or the next two chapters that we're going through. So we'll meet to talk about those, and just recognize that this exam, it's a bit lengthy because it's 4 chapters, but everything is related. Try to keep that in mind when you're studying, when you're going through the material, when you're reviewing the material. It's all connected, right? All of this stuff is one thing leads to another. And let me know if you have any questions as you're going through it, and I will look out for any questions. I'll keep answering emails, and hopefully you guys will be fine, and I'm sure you will be fine. And I guess I will talk to you guys on Wednesday if I don't hear from you sooner.
All right. Well, one question, the
Sure.
the COVID vaccine, is that
Sure.
like part of what you were talking about? Like the like if you're exposed to COVID and then you also get the vaccine,
Mhm.
was that kind of like what you were talking about? Like, because I'm just
So yeah, so initially what they found with the first round of the vaccine was that people who had severe reactions to the vaccine probably had not been exposed to the virus, right? And the people who had been exposed to the virus didn't get a very strong reaction to the vaccine because that was their secondary response, right? The vaccine triggered a secondary response in them, which they already had all these antibodies built up, right? So that's, if you haven't been exposed to it, the vaccine is essentially triggering the primary response. so that hopefully if you are ever exposed to coronavirus, you'll have that secondary response and your body will fight it very quickly. And now with the booster, they're saying basically those memory cells, they're not sure how long they'll stick around for, right? So that's the point of a booster. Like we get a tetanus booster, right, every 10 years or
Yeah.
so. It's because the memory cells only stick around for a certain amount of time. And so you want to just keep boostering them. You want to just keep making sure that you have that army ready to go in case you are ever exposed to that.
Because I was exposed to COVID. I had COVID.
Mhm.
I had mild symptoms, but
Yep.
when I got the vaccine, I had symptoms worse than the actual COVID. So I
Right.
was wondering, I was like, weird. It's like, because I was actually laid up for 2 days from the vaccine, but when I actually had COVID, I was just feeling like down. So it was
Right.
weird. That's why when you were talking about it, I was just wondering, like, could it have been like a false positive then? I don't know.
It
Because the
could
way
have
you
been, it
talked
could have
about
been, it could have been, there's all these different strains now too,
it, yeah,
right? So what
that's true.
happens is those antigens on the outside mutate after a while, right?
Okay.
That's why we need a flu shot every year because the antigens are different.
They
Um,
mutate, right? Constantly
yeah, so they
mutate.
mutate, right? So now there's different strains of COVID that have slightly different antigens on the outside. So maybe whatever you got infected with had slightly different antigens than the vaccine.
Oh,
You know what
okay.
I mean? The
Okay.
vaccine's not going to catch um, every single type of coronavirus. So, I mean, that could be the case too. It could be that whatever you had was a different kind of subtype, if you want, of the coronavirus, and then the vaccine hit you hard because it was something you weren't exposed to.
Oh, okay. Yeah, because the way that I got it is when this all first started.
Yeah.
So I think that was what, in the April of 2020.
Hmm.
And I just got the vaccine this year. So I probably like had the mutated vaccine or
Right.
whatever. So, okay, because I was just a little curious when you were talking about that. So
Yeah. Yeah. Absolutely.
all righty.
Absolutely. All right.
All right. Well,
Well,
you guys have a good weekend.
you too.
I have to go now. I have to go help my father. A tree fell on his deck.
Oh, yeah, it was windy here last night too. Well, good luck.
All right. Bye, guys.
Bye.